Welcome back. So now let's take a look at some of the system calls and library functions for dealing with processes. As you saw in the previous video, if you looked at the output of top, or if you ran top yourself on your own virtual machine, um, you saw that each process has a numeric code associated with it, its process ID. These are unique, so every process running on a system will have a different ID, and that's how, with various system calls that we might use, we identify the process. So there is a system call called getPID, doesn't take any arguments, and it returns the process ID of the current process. PID underscore T is the type it returns. That's simply a type def or an alias for some integer type. That might be something like unsigned short or int or so on. We don't typically rely on the precise type. That is, on one operating system, it could be a 16-bit integer. On another, it could be a 32-bit integer. But we use this alias to make our code portable to different Unix-based operating systems. Besides getPID to find my own process ID, I can also call getPPID to find the process ID of my parent process. We'll see more about parent and child processes in just a minute, but this is the process that started us. So for example, if I'm in the shell and I run ls and press enter, while ls is running, it has its own process ID, which getPID would return, and getPPID would return the process ID of the shell that started ls. So we want to be able to do things with processes, and the main things that we need to do to have a working operating system where we can do things is to be able to create new processes and to be able to terminate them. From our point of view as a programmer, we can think of a process as being in one of three states. It could be running, so that means the process is executing right now, or the process from its point of view is executing, but actually the operating system has scheduled another process to run right now. So the process that doesn't currently have control of the CPU, we still say is running. It will eventually be scheduled by the kernel and chosen to execute, and then it will actually do things. A process could be stopped or suspended. We'll see more about that when we talk about signals in lecture 14. But when a process is in this state, it won't be scheduled again until something happens to make it not be stopped. And a process can be terminated, meaning it's stopped permanently. You might think that's the end of the process, but it turns out the operating system still has to keep around some information about the process for at least a little while. So to terminate a process, one of three things has to happen. Either the process receives a signal, we'll see more about that in lecture 14, and that signal is set to terminate the process. Segmentation fault will be an example of that, or the interrupt signal that I get when I press Control-C on the keyboard. Another way a process might terminate is by returning from main. And then finally, a process can terminate on its own by calling the exit function. Exit is a C library function. There is a syscall underneath it called underscore exit, but exit itself is a library function. It takes a numerical exit status. By convention, an exit status of 0 means the program terminated normally, and non-zero means there was some kind of error. So for example, if I run ls and everything goes well, its exit status will be 0. But if I run ls and give it a file name or a directory name that doesn't exist, it will have a non-zero exit status indicating the error. And if you look at the man pages for various programs, you can see what the different exit statuses they return are, the different kinds of errors they indicate. Some processes might only return 0 or 1. Others might use that exit status to encode exactly what kind of error happened. Also, in main, if you return a number, remember main is defined as int main, and then possibly arguments or possibly not. If I return a number from main, that is going to be the exit status of my program. So I don't need to call exit at the end of main. That kind of automatically happens when main returns. But if I want to exit my program early from within another function, for example, if I detected an error and need to stop the program, like in lab 2, then I would call exit to do so. So notice you call exit once, but it never returns. Its return type is marked as void here, but the line after the exit will never happen. It terminates the program. Okay, so that's how you terminate processes. What about creating them? That seems to be a much more interesting thing to do. Well, there is a system call called fork. Why fork? Well, we'll see a little bit about that when we look at process diagrams. So fork takes no arguments. It returns a number. Its purpose is to create a new process. The new process will be a clone of the current one. So it will duplicate the currently running process. Well, typically if we're creating a new process, we don't want to have just two processes doing the same thing. So fork's return code, or its return status, indicates which process we're in. And then based on that, we can write a conditional in our program to do one thing in the original, one thing in the duplicate. So rather than original and duplicate, I'm going to refer to those as the parent process, the one that called fork, and the child process, the new one that was created by fork. So fork in the child will return 0. In the parent, it will return the process ID of the child. Process IDs are always positive, so we know that we can tell the difference there. So the child is, again, a duplicate of the parent. It gets a copy of the parent's virtual address space, but it's not the same address space. We'll see an example of that in a minute. It gets a copy of the parent's open file descriptor. So if the parent process has opened a file, that file will still be open in the child process, as long as we haven't done anything else in the child process to change that. And, of course, the two processes have different process ID. So those are the differences between them. And then, based on the return value, we might write a conditional to have more differences happen. So fork is pretty interesting and confusing because we call it once, the parent process calls it, but fork returns twice. Once to the parent process and once to the child process. So here's an example of using fork. Notice this is the capital F version of the function. This is a wrapper for fork in the CSAPP header and C file. In particular, the wrapper does some error checking and terminates the program if there was an error, because besides returning 0 for I am the child, or the process ID of the child if I am the parent, it might return a negative number, meaning it failed. So in order to avoid having to consider that, we're using this wrapper function that just terminates if there was a failure. So we have a variable of type PIDT called PID, process ID. We assign to that from fork. And then in this if, we check if it is equal to 0. If the process ID returned from fork is 0, that means we are the child. And we'll do this code, print something, and then exit. Otherwise, we are the parent, so we will do, we will not go into this if, we will come down here, we'll print a different thing, and exit. Notice that this child process has an exit here as the last thing. If I didn't have that, then what would happen? Well, the child process would print child. It would come out of the if and continue on to this code. This code, although it's labeled as parent, it's really just what happens if this if either didn't execute or finishes executing. The exit here lets us keep the two separate so that the child process doesn't go on and continue executing code that's only supposed to be for the parent process. Often you will see this written as an if else to accomplish the same thing. So these two things, the child and the parent, are executing concurrently, and we can't predict the order in which they will execute. That is, when I ran the program this time, I might get the message about the parent first and then the message about the child. The next time, I might get those in the other order. I might have part of the parent process, the child process run, then part of the parent process, and then another part of the child process. We wouldn't really see this in this program because they only do one fprintf each. But if I were to do two printfs here in the child, it's possible that the parent would execute in between those two. So these two processes are running concurrently on the system. The two processes have duplicate address space, but they are separate address spaces, separate virtual memory. Meaning, after this fork call happens, whether we're in the child or the parent, this variable x has the value 1. Then in the child, x is incremented. The child has its own copy of x now. So in the child, x will become 2. In the parent, we have a separate copy of x, which we're going to decrement, and it will become 0. So in our message, the parent prints that x is 0, the child prints that x is 2. Notice that this plus plus and this minus minus are happening to different copies of the variable, because after we do the fork, each process has its own memory. If you remember back in the videos on virtual memory, this is sometimes implemented using copy on write, so that we don't actually have to duplicate everything right away, but only when things are changed. So the moment we do this plus plus x, then the child process would get its own unique copy of x. Also, notice that both of these things are printing to standard output. The standard output is a file that was open in the parent process, and it remains open in the child process. So standard out refers to here the same file. If we want to change what standard out refers to in the child process, there are ways of doing that as well. So we can model what happens with a fork to get an idea about what's going on with different things running concurrently and what the possible orders of outputs we might see by making a process graph. So this is a graph in the graph theory sense. So we have vertices or nodes, which indicate that a statement is executing. We have a edge or an arrow from one node to another, meaning that the first one happens before the second one happens. And if we want, we can label those edges with particular values of variables so we can tell the difference between different ways we might go. If we have a printf, we might label that vertex with the output it produces. And each graph is going to begin with a single vertex with no edges coming into it. So here's an example. This is the program we were looking at a minute ago. We start out with main. Main calls fork. So this is an edge indicating that main is called before fork happens, which should be obvious here because, well, the call to fork is within main. Main had to start before fork could. Fork now returns twice, once to the child and once to the parent. So in the child, we will do this increment, x will become 2, we'll call printf, get our message, and exit. In the parent, we will do this decrement, x becomes 0, we call fprintf, and then we exit. So if you look at this graph, let's relabel it so that we can give a unique name to each node in the graph, A, B, C, D, E, F. The arrows in the graph indicate that one thing has to happen before the other. So A, main being called, had to happen before fork was called, as we said. The call to fork happens before the call to printf. The call to printf in the child happens before the call to exit in the child. The call to printf in the parent happens after the call to fork and before the parent's call to exit. So a feasible ordering, that is an order that we could actually see occur, is any in which we arrange all of these things, A, B, C, D, E, F, and every arrow in the process graph goes from left to right. So A to B, left to right. B to C, left to right. C to D, left to right, and so on. An infeasible total ordering is one where there is an arrow that goes from right to left. So in this example, I can't have this order of operations occur because F, that is the child's call to exit, has to happen after E, the child's call to printf. If we did the exit and then the printf, that wouldn't work right. That simply couldn't happen. So we can have this order. It is possible that E here, the child printing, happens before C, the parent printing. Those could be the other way around, but I can't have something within one of those processes travel back in time, as in this example. So let's take a look at another program. Here's one that does 2 forks. Now, it might seem that this is a little bit simpler than the previous example in that we don't have the if and so on. But remember, each of these calls to fork is going to make a copy of the process, and both the parent and the child process will continue to the next line. So in our output, we can expect to see L0 once. That happens before the call to fork. L1 will happen twice. Both the parent child and the both the parent process and the child process will execute this line. So we'll see L1 in our output twice. Then we fork again. Now remember, when we get to this point, there are 2 processes running. So 2 processes are going to call the second fork, each time creating a new child process. So we're going to end up with 4 processes executing this by command. So we can model that as a process graph like this. We have the printf of L0, then we do a fork in the parent or the child process. I haven't really specified which is which because since I'm not actually checking the return value of fork, there's not really a difference. But each of them will print L1, then each of them will fork and print by. So we could have a lot of different orders these things happen in. You might expect to see L0 and then L1, L1, and then by. But we could get an order like this. L0, then we fork, and let's say this is the child process. The child process calls printf for L1, then forks. Now we have these 2 processes, each of which print by, and only then, perhaps, does the printf in the other process, the original parent process, run. And then it prints L1, forks, and 2 bys. So we could see this order. What we can't see is this order. There's no way we could get a by in this program without having had an L1 first. So if our first by comes before our first L1, that's an infeasible ordering. That would require, if we were to draw these out, that would require us to have an arrow going back in time from the L1 to the by, which doesn't happen. We could have a situation like this. So these examples, by the way, are all in the 13code.tar.gz. So I'll recommend trying it out, running it, and seeing what output you get. There are examples here of what the output might look like, but because things are running concurrently, uh, your results may vary. But you will get one of these feasible outputs and not an infeasible output. So here, I call fork. Now I am checking its return value. If fork is not equal to 0, that means I'm the parent. Fork returning 0 means I'm the child. Fork returning non-zero means I'm the parent, and the return value happens to be the child's process ID. So in the parent, I will print the L1 message, call fork again. If I'm still in the parent, I will print the L2 message. And what about the child processes? Well, they will go on down here and print by. So we can model it with this diagram. We have the printf, then the fork. The parent process over here will do one thing. The child process, if fork returned 0, will go straight to printf by and then into the function. So that's this node. But in the parent, after we do the printf of L1, we call fork again. That's again going to give us the parent process and the child process. The parent process, when fork returns non-zero, will print L2, then fall out of this if and print by. And that second child process will itself print by, because we didn't go into this if, and we just kept executing down here. So there are different orders of output we can get. As long as L0 comes before L1, L1 comes before L2, L2 comes before this last by, this by in the parent process. This by in the child process, first child process, has to come after L0. This by in the second child process has to come after L1. So this would be a feasible output. L0 in the parent, L1 in the parent, then maybe by from the child. Then we fork again and by from the second child, then L2 in the parent, and by in the parent. Whereas this is an infeasible order. We can't have L2 as the last message. We can't have 3 bys before L2, because this last by, we have an arrow from L2 to by. L2 has to happen first. It came earlier in the code, and it's in the same process. All right, so in a next video, I'll talk about reaping child processes, because it turns out that when a process terminates, it doesn't completely go away. There's something we have to do to make that happen. But we'll see that later. Thanks for watching.